today. Before I get started, of course, I've published all the recordings. Okay, even yesterday's recording is already published, the video recording. Okay, so that you may have another opportunity to be able to catch up with whatever you actually miss. Okay, I want to welcome you to this lecture that we actually call difference. Okay, the other time introduce you to time series analysis. This is going to be part 5 of the time series analysis topic that we started. Okay, so what we want to do today that we call difference. What is the essence? Why do we need to difference? Okay, it's just like in regression analysis, and somebody asks, why do we need to transform our model? Of course, we normally embark on transformation of model if there's a violation of assumption. Okay, so in time series analysis, we normally consider differencing if there's a violation of stationarity assumption. Does that make sense? And of course, before now I walk you through what the assumptions are. Like we expect the mean and the variance to be constant over time, and not only that, we expect the autocorrelation, at a particular lag, at lag 1 to be the same or true, lag 2 to be the same or true, and so on like that. So because of that, the reason why we so I'm actually saying this topic as an intervention, a model, whose assumptions are violated, and the assumption that are violated is stationarity assumption, and how do we fix it? So it's an intervention. Okay, and let me tell you this: when we want to fix, we're actually going to, we want to look at how many times do I need to difference. Is it one time? Is it 2 times? Just like we have a problem in real life, and we basically want to know what is going to be the the action, or let me say, that will commiserate, that we're going to take, that will commiserate, to solving the problem. Okay, so because of that, I'm actually going to walk you through, the mathematical way of differencing force. Okay, now take a look at the set of data that we have, which is this guy here. Okay, these are the set of data that we have. Let's assume that the data set that we have is not stationary, and we now want to difference. Okay, then we go to difference by lag 1. By lag 1 means the second data point minus the first data point, the third minus second, and so on like that. That was what led to this. Does that make sense? That is differencing at lag 1. Why do I need to go for that? Because how do I know that, okay, the effort that I've put in, there's a problem, right? And the effort that I've put in is not working. How am I going to know whether it's working or not? I'm actually going to investigate whether assumption hold. Maybe after differencing, okay, by way of lag 1, which we call the first differencing, we realize that effort was not enough to bring the to bring back the stationarity that is required. Then we now want to continue differencing at lag 2. Okay, so if you basically see what is going on here, okay, it's differencing at lag 2. So you're gonna that one is now gonna, lag 2 means they're gonna be 2 lag apart. Okay, the lag 1 is 1 lag apart. Okay, in the lag 2, what we're gonna do is just gonna be y3 minus y1. Okay, and y4 minus y2. So that is the idea of the lag 2. It means that this, they're basically going to be 2 lag apart. Does that make sense to you now? How the difference in work, mathematically speaking. Okay, the next thing we want to do now is how do we actually do this in R? We don't want to waste time. What if we have like 1,000 data set? Right now we only have 6, right? Manually, doing it manually is going to be easy. What about 1,000 data set? And that's why we need software. The software, whether MATLAB, Python, R, SPSS, or whatever, they all going to, aid our computation. They don't add anything to, because they say the formula behind the scene does not change. Does that make sense? Now, I have data set 1, 2, 3, 10, 100, 1,000. Okay, which is the one that I actually talking about here. And we want to difference, using the hard code. Okay, we believe that the TS, okay, is not stationary. Okay, and we cannot proceed to fitting the autoregressive module or moving average module because time series module rely on the assumptions of stationarity. Okay, now if I want to difference, I'm just going to write DIFF, or in a lowercase. Okay, I use TS to save my data. What do I have? By the time you now press that, you're just going to have 11790 900, which is basically what we got here the other time when we did it manually. Does that make sense? That is the first differencing. And I can write DIFFTS, 1 to show the lag, but it doesn't matter for first differencing. But if I want to go for the second day at lag 2, I have to, disclose the lag equal to 2. Okay. Now we have a notation. Please pay attention to the notation. I know you have seen that notation before in math. This particular guy, that guy is talking about the, differencing. When you see what is the difference between YT and this guy, okay, YT is not difference, but this guy here is different. When you see that data, it means differencing at lag 1. Does that make sense? That is what we mean by data YT. So which means the 11790 900 right now, they are no longer YT, but they are data YT. Does that make sense? So that data here means differencing, first differencing, because we can as well, maybe let me see, you can as well have something like this. Do you see that? When k equal to 1, that is for the first differencing. When k equal to 2, you're actually going to have data square YT, which means differencing at lag 2, and so on like that. So you need to pay attention to all of that. Okay, you see that one now? Okay, we can write it that way. We can write it can be subscript, it can be superscript. Okay, now you can now, I told you the other time, if you want to do it at lag 2, what did I say? TS, lag equal to 2. For that of lag 1, you may decide not to. Arrow will automatically, if you don't specify lag, Arrow will do it to lag 1. Does that make sense? Okay, so you can see that to lag 2 now, we got 2897990 that we have, here, as you can see. Now, can I say now, can I actually believe now that, of course, you know how to difference, whether using, manual way or going by R. That makes sense, right? You know how to difference. Now, I told you differencing, it's like we basically want to solve, there's a problem of, assumption violation of stationarity, and we basically want to restore that. Okay, now I want us to go back into this, fit a model to this time series. If you take a look at this, you have a time plot that look like this. You generate a time plot from a time series data of a sample size 1005. And that's what you can see. If you take a look at what this guy here, there's a violation, looking at this. Because you know why? Do you expect the mean? Is the mean constant over time? It's an increasing. That was why I said, no, the mean is not constant at different time. Okay? If you really want to know, graphically, to see whether your data set, your time series or data actually, maybe there's a violation of stationarity, you can actually construct a time series plot that we call a time plot. Even though we also have some tests, that we can conduct. And I'm still going to let you know. This is also a graphical way. We also have standard statistical tests that we can actually or use. We call it a unit rule test, the Kifula test and stuff like that. But I'm still coming into all of that. Okay. Now they are now asking you a question whether is this series or stationary? No. Does that make sense? And the reason why it is not stationary because the mean is not constant at different time. Now, let me tell you this. If I'm driving, right, and I see a red light, and I decide to ignore, what are the possibility of things that could happen? Like I'm driving, whether in the United States or in anywhere in the world, and they have a traffic rules, right? And everybody agree that when it turns red, don't go, right? And I decide to go, what is going to happen is either there's going to be a crash. Okay, if there is no crash, then I can be ticketed. I can, be pulled over by the police and get a ticket, then get punished. But the worst that will happen is to have, is a crash, and which is maybe disastrous. Now the question now is, if I have this particular plot like this, where it is very obvious that there's a violation of stationarity assumption, and I ignore that. There's a problem, but I ignore the problem. And I decided to, fit an autoregressive model. Now, I needed to pay attention to the first one. Can you see the ACF, right? Now, if you take a look at this ACF, this guy here, it doesn't really look as if it's decaying exponentially. Does that make sense? The way you are looking at that. Then, if you look at the partial ACF, of course, yesterday, I told you what the partial ACF actually indicate, right? When a particular, when it's cut off after, and maybe at lag 1, at lag 2, when it cut off, it means lag 1, is, which means after lag 1, if it cut off, it means lag 1 is okay for it. Now, take a look at this now. We figured this and we believe that, it's cut off at lag 1. As you can see, it cut off after lag 1, I'm talking about this guy now. You can see this for lag 1 and it's cut off after lag 1. And that was why you are fitting. What are you fitting? You fitting a arrow of other one, right? There's an arrow of other one that you are fitting because of the fact that you look at the partial ACF plot and you realize that the partial ACF that cut off after lag 1, so which means lag 1 is appropriate, right? Okay. Now, and that was why I said after using the ARIMA function to fit the model, we obtain the following. Why do you go ahead to fit the ARIMA to be able to obtain this? Of course, I walk you through how you can derive this guy here. What actually gave you, you know, uh, you know, what gave you a clue to fit an AR1 is because of the fact that you see that the PACF cut off after lag 1. Does that make sense? Okay. Now you fitted that. Okay. Of course, this is another way of writing. I told you there are two ways of writing the autoregressive or model. Okay. Now, if I have this guy now, don't forget, I ignore what? I ignore violation. I just go ahead and I fit auto-regressive model of order 1. Okay. Now, this is what we want to do. We now want to investigate to be able to see whether the autoregressive model that I've used will actually do the job by conducting residual analysis, right? Okay, that's what we do. We want to do diagnostic study now, where we basically want to use residual. So don't forget, we actually going to do what? We expect when we construct, when we generate the autocorrelation function plot for residual, what do we expect? If residual behave like a white noise, what do we expect the behavior to be? Is all of, at any lag, it should be zero, right? Autocorrelation function plot of residual, okay, have to be zero if residual is a white noise. Okay, let's see. Now, if you want to do that, this is the code in R. Okay, this guy is the code in R. You basically want to figure out, you want to plot, you want to generate autocorrelation function for residual. Okay, assuming autoregressive module of order one. Okay, that's exactly what you want to do, and let's see what is going to come out. Oh my God, take a look at this guy. Does it look like all the autocorrelation value within zero? No. That's how to know that that is not a good model. You know why? Because the assumption is violated when you've ignored that. It's just like somebody committed an offense in the state, in Minneapolis, in Minnesota, and the person run to New York. Okay, the person run to New York. If New York, if Minnesota alerted New York that, okay, we got a criminal, we got a suspect in your state, okay, then what New York is going to do, okay, is to send that person back into Minnesota, and the person is to be tried under Minnesota law because that guy broke Minnesota law. Okay, if New York decide to ignore that and use their law to try the suspect, even though if New York was able to establish the fact that this guy committed the offense, whatever decision they take will be null and void. Because you know why? New York does not have a territorial jurisdiction under the law to try the suspect because the suspect did not break the New York law. The suspect broke Minnesota law. That's exactly the same here. Like, okay, we realize that looking at the data set, or the time series data set, the seasonality assumption is already violated, and there's no yardstick at all, to actually move forward, feeding time series models, because the time series models, they basically rely on the assumption of stationarity. Does that make sense? As you can see now, constructing the autocorrelation function plot of the residual, we can see that the autocorrelation values at different lag is not approximately zero, as you can see, and that is telling us there's a problem. Okay, and that was why they're asking you here. Okay, what if I gave you this in exam? I give you something like this. I call it ACF of residual, and I ask you a question: do the residual of that model behave like a white noise? Your answer is going to be no. The only way residual can behave like a white noise is when the autocorrelation, at different lag is within zero. Does that make sense? But right here, this is very obvious. Go ahead. Oh, yeah, there was one we did. If the majority are within zero, because we actually using a 5% level. You remember we did something like that the other time. Yeah, right. Mm-hmm. Those of you online, can you still confirm again if you can see hearing me clearly? Those of you
Yeah, we
online.
can see and hear.
Okay, is there anyone who want to ask question among those of you that are online? Is there any question at this time? Okay, you are all good, right? Okay, now I'm going to move. Now, when this happen, what are we going to do? There's a violation, right? Then we're going to difference. We want to difference now because the diagnostic testing we've conducted by virtue of residual analysis has already indicated there's a violation, right? And we cannot trust that model. Then we now need to remove the increasing trend. The other time, what causes the violation was the fact that the mean was actually increasing over time. So we need to remove that by taking the difference. Does that make sense? If you want to take the difference, now I told you the other time, our differencing is an intervention. Now we're going to first start by differencing at like 1. Okay, take a look at that. Look at that code. Okay, YT1 initially, uh, YT was actually that I said that is problematic, because there was a violation of stationarity assumption because of the increase in mean, okay, over time. And can you see what I'm doing right now? I want to generate, I want to difference, I call it YT1, and I write DIFFYT. It means I want to difference to like 1. Does that make sense? Okay, then I want to plot again. I want to generate time series plot again. Oh, let's start celebrating now. You see that now? This is not increasing over time anymore. If you want to compare this guy with the original plot of the series, I'm going to show you the original plot of the series. Can you see the original plot of the series? Okay, this is the one we generated when we have no difference. Okay, so but after differencing now, I'm going to show you what we got after differencing. Can you see what we got? So if you take a look at this guy now, of course, you're basically going to see, this is not, this like a stable. Okay, this is stable. Okay, now the next thing we want to do, okay, we now want to generate both ACF plots and the PACF plot for the new data set, for the difference data set. Oh my God, take a look at this guy. This is looking so nice as the autocorrelation is decreasing exponentially to 0. Okay, and of course, this guy now, it cut off at like 1. But let me tell you this, the other time, even with the fact that there was a problem, the partial ACF still indicate that it cut off after like 1. The only plot that indicates a problem was the ACF. Does that make sense? The ACF are the time series plots, the time plot. Okay, they were the one that indicated the problem. The partial autocorrelation did not give us, a sense that there's a problem, because look at what I have here. It cut off after like 1. It also cut off after like 1 the other time. So take a look at that. Okay, now after using that RIMA, okay, we're now gonna fit AR1 now. We're not gonna fit AR1 now, but don't forget, we are fitting autoregressive model of order 1 now for the difference data, not for the original one. Oh my God, this is what I'm actually gonna have. Okay, why do I put data? You can see data. Okay, we have to put data at both ends to indicate that your data set has been difference. Does that make sense? Okay, so that is why you are saying data. So I expect that if you want to present the model to me, okay, of a differential data set, this is how you're going to present that. Both YT and YT minus 1, they're going to have the data. Does that make sense? Whether you are, if the partial autocorrelation function as suggested, ARO of order 2, you're also going to have that data repeated in all of that. Okay, that makes sense, right? The same way we're fitting model, that is the same way we're gonna, do that now. Okay, now we know we fitted this model now, right? Okay, we don't rush to take a decision. We need to do diagnostic testing. It's just like, oh, this guy came to my hospital for treatment. He's seeking for treatment, and when he came in, I diagnose this guy, I realize that there's a problem, right? The time plot. So, oh, there's a problem. And after treating him as a doctor, what am I going to do? I need to investigate again whether my intervention has worked, right? That is what we want to do now. We fitted a model now. All right? Now, what we'll do now is we basically want to conduct a residual analysis again. Okay. Oh, I've treated this guy. Okay, let me see whether this guy is better than the way he was when he came in to my clinic. Okay, now I want to do the same now. What am I going to do is to conduct autocorrelation function on the residual. Okay, and this is the code. Okay, on the residual MOD2. Don't forget the data set that I'm actually using is a difference one. Okay, at lag 1, and let's say the ACM. Oh my God, take a look at this guy now. Take a look at it. I think this is the question you asked the other time, right? Take a look at this guy now. The majority, you can see that. Then it means the differencing is already working. Does that make sense? That's what it means. And we can now conclude that residual behave like a white noise. Let me tell you this. A module is good as assumption put into a module. What make model to be great is when assumptions are not violated. So the moment assumptions are violated, okay, it's like dead on arrival. You don't even need to entertain it because you don't have. It's like somebody who do not have authority to arrest, and the person now go and arrest, even if, that person has really done. So the most important thing is, okay, maybe you see somebody committed crime and you intervene, but you're still going to involve police, right? You are not going to take law into your hand. That's what I mean. Okay, now a module is good when assumptions are not violated. And of course, in statistics, we actually have a way to investigate whether the modules we have fitted, they're actually going to do a great job. Okay, so take a look at that. Okay, now, do you know that after we have justified the model by way of investigating whether assumptions are violated or not using residual plots, using the, the autocorrelation function of residual, we can see that residual behave like a white noise. It means everything is fine. Then I can use my model to make a prediction. Don't make any attempt to use your model to make a prediction if your model has not been validated. So what we have done, we validated the model, we've confirmed the model, then we can now use the model to make prediction, because this prediction, the recommendation from this could go into policy formulation. And we don't want a situation where we're going to take a wrong decision. We don't want to mislead. And that's why we're doing all what we're doing right now. Okay, now what we want to do now, don't forget when we started, the data set is 1005. Let's confirm that. The sample size in the data set is 10. Can you see that? It's actually, give me 1 second. It's sample size of 1005, which means the last data point is number 1005. Does that make sense? Okay. Now we may want to make a prediction of the number 1006. Does that make sense? Because what we do in time series is to use the variation in the past to explain the variation in the future. I remember one former American president called JF Kennedy. Has anybody heard about JF Kennedy? JF Kennedy said, and I quote, he said, "We cannot correct the past, but we can run perfectly the future through the mistake of today." Of course, through the mistake of today, we can run perfectly the future. Then it means we want to use the variation in the past to explain the variation in the future. Okay, now we want to go into the prediction now. We can trust our model because right now we've validated our model, assumption hold. Okay, even though there was a problem initially, but we fix it by differencing to lag 1. Okay, And if like one doesn't work, if we conduct a residual analysis, generating the ACF plots for the residual, and we realize that it does not behave like a white noise, we can go back to the data set and difference again and start the all process over and over again. Okay, now like I said, the last data point is 152.2164. Now we want to make a prediction for 1006. I mean, how do we do that? When we difference, take a look at this code. Okay, can you see code? Predict. Do you see predict? What module am I using? MOD2. Then n dot ahead equal to 1. Ahead equal to 1 means, right now we are in 1005. I want to predict for the next one. It could be the next day. Okay, if I want to do that, okay, take a look at this guy now. Y cap 1006, which is the predicted, what we want to predict, equal change, equal this guy plus Y1005. Okay, you may be, of course, we already know Y1005. We know this guy from the last data point to be this. That's what I plug in here. But the question now, how are we going to figure out this guy? Okay, I'm going to show you now. You're going to see how we're going to figure that out. When you can get that directly from the code. Take a look at this. I'm going to show you something now. Okay, now from the code, let me do this first so that you can see. Okay, from the code, okay, we got this guy. Do you see this guy? That code, you know what that code is giving you? It's giving you the data Y cap 1.40994. Okay, to 2 decimal, that will be 1.41, right? Okay, so which is this guy here, which is the one that we're going to plug in here, which is the one we've plugged in here. Does that make sense? Okay, you saw the code, right? In the end, what we predicted is actually this guy. Any question? And do you know that this guy here that we got, from here is more or less a change, which is a difference between 1006 and 1005. That is the difference. That's what we call a change. Okay, so that is what you are seeing now. So in the end, we got 153.63. Okay, so which is what we have done. But you know what? What if I want to use my model that I feed it to predict? The model we feed it was this, which can also be. Now, I now want to do something now. He said, predicting, forecasting the next observation, right? Now, this model here, okay, is the same thing as this guy. How? I'm going to walk you out now. Give me 1 second. You're going to see. I'm going to take the picture, and I'm basically going to use the board. You're going to see what I mean. Okay, you're going to see what I mean. But before I go into the board, okay, I first wanted to take notes. I'm going to show that this can be expanded, okay, to basically give us this, okay. And the moment we have this, if I want to predict YT cap, I need YT minus 1 and YT minus 2. See, YT, if YT is 1006, of course, the YT minus 1 will be the last observation, 1005, and the YT minus 2 will be 1004. Does that make sense? What I'm trying to say now, this guy is this. This guy is this. Okay? This guy is for 1005, the last value in the data set. Does that make sense? Okay. And don't forget what we want to predict is for Y1006. Do you know that you can just go into your data set and look at this, the last two values, and plug them in here? But if you want to record them in R, you can use this. But don't forget, if you want to record observation 1004, 1005, you're actually going to use the previous data, YT, the one you have not difference. Does that make sense? So now, but what I want to show you now, how does this guy, okay, become this guy? How does that become that guy? That's what I want to show you now. And I'm going to share, I'm going to stop my whiteboard. I'm going to share, I'll stop my share, and I'm going to share my whiteboard. Give me 1 second. I'm going to take the picture so that I can stop my share. Okay, I'm going to stop my share. Okay, I'm going to now. I'm going to make board. Those of you online, can you confirm if you are seeing the board? Can you see the whiteboard? Okay.
Yep.
Thank you so much. Okay, now the fitted model. Okay, the model that we fitted. Give me 1 second. Okay, now the model was actually data YT equal 0.0288 plus 0.82 data y data YT minus 1. Okay, now I want to be able to show you that this is also going to be 0.0288, okay, plus 1.82 YT minus 1 minus 0.82 YT minus 2. Okay, so that is what I basically want to show you now. Okay, now the other time when I was explaining something to you, I said, recall, I said there are YT, okay, there are YT, okay, let's say for 1005, for instance, if this one is 1005, it's going to be 1006 minus 1005. You remember that I actually said this, okay? Change in Y1005 is going to be the next one minus the previous one. Now, because of that, I'm actually want to come into the generalization, okay? If I have a data YT cap, okay, it's basically going to be what? Okay, so I have a data YT here. This is like a T, okay, and this is actually 1006. Okay, now when you take a look at this, it's more or less going to be YT plus 1 minus YT. Okay, if you take a look at what I actually have, okay, so if my data YT, okay, equal to that, okay, so my data YT is YT plus 1. You can see this one of 1005, okay, this one go up by 1 and you actually have that guy. Okay, now if that is what we actually have, okay, when you take a look at what I have here, if I want to rewrite this, in a similar version, okay, I can put yt plus 1 minus yt, okay, and if you take a look at this, delta yt minus 1, okay, is going to be yt minus, does that make sense? Look at that. This is going to be this yt minus that. Okay, see, yt minus 1, yt minus 1, and this is going to be yt. You see that now? So in that regard, okay, which means I can plug in here. Okay, you can see I can plug in yt, okay, and yt minus 1, and here where we have delta yt, I can plug in this and that. Okay, so if I continue to go like that, let's say for instance I have t minus 2, right? Okay, and this is going to be yt minus 1, okay, minus yt minus 2. I can continue to go all the way. Does that make sense? Okay, so now what you're now going to do is, since this is what you have initially, all what you're just going to do, and we want to have our result in terms of yt. You can see the result is in terms of yt minus 1 and yt minus 2. So if you take a look at this, I plug in yt plus 1 and yt, okay, and here I plug in this and this. Okay, now in another version, okay, what you're basically going to see is that, I can at the same time, for this one to be delta yt and equal to this, if I go back by -1 like here, okay, I can just, okay, this equal to this and that. Does that make sense now? So by the time but it doesn't really matter. It is not compulsory. Like if this is confusing you, okay, if I were you, you can leave it this way. You can leave your result this way. And if you leave your result this way, of course, how we plug in the other. But what I'm just trying to show you is just like another way to do it. Okay, just another way to do it. Okay, so you don't need to do any rigorous, derivation. Give me 1 second. I'm gonna share my whiteboard. So you don't need to do any rigorous. It's an applied course, so it's not a theoretical course. But I'm just trying to show you that, okay, another way to about, okay, so that okay, so that was I think I've already walked you through all of that. There's one way of doing it, 153.63, and another way of doing it is just to go by, okay. So, and you're basically going to see, like in the data yt, okay, what they actually plug in, okay, data yt minus yt minus 1, okay. So, and here I can write that as YT minus YT minus 1 equals 0.0288 plus 0.82. Okay, if we want to go similarly, it's going to be YT minus 1 minus YT minus 2. That's another way. Want to go, you can just simplify that, and before you know, you're going to find yourself, okay, in that. Any question? I think that is all what I have for you. I think because I have time, let me, in case those of you that may want to, let me just quickly show that so that you can. Now you all know this one now, right? Okay. Now you have it in this form. There are YT equal to this, and there are YT minus 1 equal YT minus 1, YT minus 2. We've already plugged them in. So you just need to collect the like times. So this equals 0.0288 plus 0.82 YT minus 1 minus 0.82 YT minus 2. So now there's a YT here. Okay, so this can go to the other side. Okay, because we want to leave our result in terms of YT. So YT equal 0.0288 plus 0.82 YT minus 1. If that YT comes, it's going to be plus YT minus 1 minus 0.82 YT minus 2. So look at this guy. So this is going to be YT equals 0.0288 plus 1.82. Okay, let me see. Yep, YT minus 1 YT. So when you factorize, so YT minus 1 minus 0.82, so which means, okay, if you have a difference, a arrow of order 1, okay, the difference, don't forget, you difference your data before you apply that. So after getting this out, by the time you plug in all this, you find yourself here. Okay, if you want to, without even R, if this is for 1006, this is going to be 0.0288 plus 1.82 Y1005 minus 0.82 Y1004. Does that make sense? You just plug in the last data in your original series and the second to the last in the original series, and that will automatically give you the estimate of that. Okay, that will give you the estimate of that. Does that make sense? Any question? Any question? Okay. In the absence of question, make sure you all stay safe and have a lovely day. Bye for now, everyone.
Thank you.
You're welcome.